Full-text search misses messy names and small typos. PG Targum gives Postgres fast fuzzy matching in Python, so name search feels forgiving instead of brittle. This is the setup you'll be able to run after this, which fuzzy matches a misspelled name against candidates and returns the best match with a confident score. I'm Professor Pi, teaching search and IR with simple Python. Names are messy in the real world. People type fast. Systems import lists from spreadsheets. A single letter off and exact match fails. That is where trigram fuzzy matching shines. It sits inside Postgres and scores how similar two strings look by their overlapping three-letter chunks. You get forgiving search without moving text out of the database. Intuitively, PG trigram breaks words into small pieces and counts overlap. More overlap means higher similarity. It is fast because Postgres can index those trigrams and apply a cheap filter before scoring. For record sizes in the thousands or tens of thousands, you get instant responsiveness. For larger sets, you still benefit from indexing and built-in operators. We will build a tiny pipeline that connects to Postgres, enables PG-RGRM, inserts a handful of messy names, runs a fuzzy lookup for a misspelled query, adjusts the threshold to see recall change, and finally blends similarity with a prefix boost to get robust rankings. This keeps the code short and the behavior obvious. First, we will confirm the database connection and driver are working. This snippet connects to a local Postgres instance using psycopg and checks the server version. The variable DSN holds a minimal connection string that psycopg.connect uses to open a session. The code block with con.cursor creates a cursor for issuing SQL commands. The query, show server version, asks Postgres to return its version string, which fetch1 reads into the variable ver. Keeping the connection object in a global variable lets later steps reuse the same session and transaction context without repeating setup. Seeing the version confirms network access and a working driver, which is the foundation for adding PGTRGM next. Next, we will create a tiny people table and load some names. This example enables the PGTRGM extension and seeds a tiny people table using psycopg. The list names is our toy dataset of slightly varied person strings, including common typos and truncations. Inside the with.con.cursor block, create extension if not exists, PGTRTGM activates trigram support in the current database. The table people is rebuilt to keep the state predictable. Then each name is inserted with a parameterized statement to avoid SQL injection. A quick select count verifies how many rows landed, and con-commit makes the changes durable. The printed total confirms our corpus is ready for fuzzy matching with PG_TRGM. Now we will issue a fuzzy lookup for a misspelled name and capture the top hit. This snippet performs a fuzzy lookup using Postgres PG trigram and returns the best match. The variable to is a misspelled query, and the SQL uses similarity name %s to compute a trigram score against each row. The predicate name $s applies the PG trigram similarity operator, filtering rows at the current threshold before ranking. Results are ordered by the similarity score S, and then by name for stable ties. And limit 1 returns the single strongest candidate. The variables best and score capture the top match and its numeric similarity. The printed name and score show typo tolerance working directly inside Postgres. Next, we will experiment with the similarity threshold to see how recall changes. This example tunes PG trigram behavior by changing PG trigram.similarity threshold within a transaction using psycopg. The first cursor sets a stricter threshold of 0.4. Then counts how many rows satisfy the fuzzy operator name % for the query Q. The second cursor repeats the process at 0.2, which is more permissive and typically returns more candidates. By comparing C strict and C loose, you see how recall expands as the threshold decreases, at the possible expense of precision and performance. Lower values include weaker matches, while higher values focus on nearer neighbors. The printed difference shows how many extra rows the looser setting contributes. Finally, we will combine trigram similarity with a simple prefix boost to improve ranking. This snippet composes a small ranking pipeline in Postgres using psycopg and pg_trgm. The query builds a CTE named S that computes trigram similarity as sim and a prefix boost PFX using name I-like for the same search text. The final select combines both signals into a weighted score, emphasizing similarity while modestly rewarding prefix matches. Ordering by the blended score and name yields stable, high-quality results, and Limit 3 returns a compact shortlist. The variables names and best hold the top candidates and the best score. The printed list and score demonstrate a tiny production-friendly fuzzy baseline ready to tune. To map this tiny example to a product, imagine a user search box for contacts. The same query flow runs on each keystroke or on submit. With a small dataset, the database handles everything. For large datasets, you keep the same SQL pattern, but add indexes and measure latency before moving to any external index. Recap: PGTRGM is a trigram-based fuzzy matcher inside Postgres. Use it when you need forgiving string search for names, addresses, or short text stored in the database. One caveat: lowering the similarity threshold increases recall, but also includes weaker matches and can increase work for the database. Next step: tune the similarity threshold and the weight on prefix matching to hit your precision recall sweet spot on your real dataset. If short, practical IR helps, subscribe and watch the IR videos.